Alright, guys. Black holes are often treated like cosmic sci-fi horror movie monsters, right? They're mysterious shadows that, they roam the galaxy and they suck everything in.
What do you mean by that?
But in reality, they're less like roaming vacuum cleaners and more like extreme physics laboratories, if you get what I'm saying. They don't chase you, they just sit there warping space-time in ways that make Einstein's equations work. And over the next 7 minutes, we'll break down what a black hole actually is. I've been making a lot of videos alluding to general relativity and solutions to Einstein's equations and black holes. But we'll talk about the different species of black holes that exist, how they form, why some Einstein field equations give them their personality, and what would happen to you if you got a little too close. And finally, why every astrophysicist secretly has a black hole poster under their pillow, right? It's so important and just so cool that everyone just thinks they're aesthetic astrophysics or whatever. But it's not just aesthetics, it's fundamental physics at work. When I was looking at my YouTube statistics, I found out that only a small percentage of my viewers are actually subscribed to the channel. So if you enjoy this kind of content, please do subscribe. It's literally free for you to do, and it helps me a lot. Thank you, and let's get back to the video. So, the types of black holes, they come in three well-defined sizes. Think of them as small, medium, and large, sort of like soda sizes. Stellar mass black holes weigh a few to a few dozen solar masses, and they're left over when a colossal star collapses. The second level would be intermediate mass black holes, and they're sort of the cosmic middle children in the hundreds of thousands of solar mass range. They're generally suspected to be found in dense star clusters, and then you have the supermassive beasts, the one we've heard of, the ones that are anchoring whole galaxies, like the Milky Way and like Andromeda. Ours, which is called Sagittarius A star, clocks in at about 4 million solar masses. Some quasars, for example, feature holes billions of suns heavy, bright enough to outshine entire galaxies. There also may be some sort of primordial black holes from the early universe, but they're still relatively hypothetical, sort of like our physics equivalent of Bigfoot or the Yeti or the Loch Ness Monster. Now, how do black holes form? Now, black hole birth stories depend on the progenitor's mass, so the star that it was born from, and its mass. A stellar mass hole forms when a star at least 20 times the mass of the sun runs out of nuclear fuel. With nothing pushing outward, gravity wins. The core collapses of the star, and the outer layers explode in a supernova. But the center keeps shrinking until space-time can't push back, resulting in a black hole. Intermediate mass candidates, on the other hand, likely result from mergers of stellar black holes inside wild stellar nurseries, or from possibly runaway collisions of huge stars before they even explode. And finally, the supermassive black holes are still pretty much a mystery. I mean, we don't know if small holes snowballed over billions of years, or did gargantuan direct collapse clouds form them pretty fast in the early universe. Either way, they snack on gas, stars, and obviously the occasional unlucky planet to bulk up. Now, I know I said that black holes form when a star runs out of nuclear fuel, but how does that exactly happen? It's not magic or science fiction, right? It's gravity doing what it does best. Winning. Every star spends its entire life fighting essentially a cosmic tug-of-war. The outward pressure from nuclear fusion inside the star pushes against the inward pull of gravity. And as long as fusion burns in the core, the star stays pretty stable, which, it's a perfect balance. We call this perfect balance hydrostatic equilibrium. But when a massive star, at least about 8 times the mass of our sun, runs out of fuel, the balance collapses. Fusion stops, but pressure then drops, and gravity then crushes the core inward because of the sheer amount of mass. The outer layers slam down at about quarter the speed of light, and they bounce off the dense core and explode outward as a supernova like I mentioned, which is one of the brightest events in the universe. But if the leftover core is heavy enough, typically if the core is more than 3 times the solar mass, not even neutrons can withstand gravity's pull. The atoms get squeezed so tightly that matter itself collapses into a single point, a singularity, surrounded by an invisible boundary called the event horizon. And that's the birth of a stellar mass black hole. After that, the black hole just sits there, right? Warping space-time around it, feeding on any gas or star that strays too close. Over billions of years, smaller black holes can merge, forming the supermassive ones at galactic centers. So when you look up at a bright star tonight, remember some of them are ticking time bombs. When their fuel finally runs out, gravity will take over completely, and what's left is one of the strangest objects in the cosmos. Okay, so what does this have to do with Einstein's field equations that I keep mentioning in my videos? Now, all black holes are solutions to Einstein's field equations written in 1915, which tie space-time curvature to mass energy. Solve the math for vacuum, no matter, just gravity, and you get different flavors of space-time, essentially potholes in the equation. One of them would be the Schwarzschild black hole, a non-spinning, neutral charge, perfectly spherical black hole. It's nice for homework, but it's pretty rare in nature. And trust me, I've done the homework on this. It's not fun. No. Anyway, another kind of black hole would be the Kerr black hole, right? Add some angular momentum to the black hole and some level of spin, and space-time gets twisted, right? Outside the event horizon lies what we call the ergosphere, right? A region where every object is forced to co-rotate. Frame dragging is so strong in this that you could steal energy from a black hole in theory. Go check out my video. I talk a little bit more about Kerr black holes and where the solution comes from, and be sure to check it out. Another example is the Reisner-Nordstrom and Kerr-Newman. These kinds of black holes both introduce electric charge, and that gives more sort of exotic horizons and even theoretical possibilities like wormholes. Astrophysical holes probably have a trivial charge, but the math is essentially just a playground for theorists, right? They just like to mess around and see what sorts of physics we can get out of it. In short, change the boundary conditions of Einstein's equations and you get a large menu of black hole geometries, each stranger than the last, and each having different implications for our universe. Alright, so let's say you ignored my advice and decided to dive into the strongest gravity well of all time. Fine, let's talk about what happens. First, you'd cross the photon sphere, the orbit where light can make a full circle. Next is the event horizon, your last, essentially, selfie opportunity. Because past that, tidal forces ramp into overkill. For stellar mass black holes, the gravity gradient between your feet and your head becomes fatal kilometers before you even hit the horizon. You're stretched into cosmic linguini, right? Which is why we call it spaghettification. Supermassive black holes, on the other hand, are sneakier, right? Tidal forces at their huge horizons are weaker, so you'll glide through feeling relatively fine, only to be spaghettified, pastified, closer to the singularity. Either way, nobody outside sees you cross. Relativity makes your clock appear to freeze. But for you, however, you can definitely see yourself going through. It's a one-way trip. I mean, obviously, you'll probably, not really notice that you're going through because you'll be... But somebody outside just sees you getting smaller and smaller and smaller. And in theory, if they have strong enough telescopes and optics, they can just continue to see you getting smaller and smaller. They'll never see you disappear. Now, finally, why are black holes so important for astrophysics? They're not like the coolest things that we see and we can just talk about them when we tell people we do astrophysics. They're mainly physics laboratories that we can't really build on Earth, right? Their mergers create ripples in space-time, which we call gravitational waves. LIGO, the Laser Interferometer Gravitational Wave Observatory, now routinely detects these, letting us test relativity under extreme conditions. Jets from spinning supermassive black holes regulate star formation in galaxies. Hawking radiation comes from black holes as well. It links quantum mechanics to gravity, hinting at possibly unified theory. Even the weird math behind charged or spinning black holes, Kerr black holes, etc., teaches us about magnetic fields, accretion disks, and maybe even the information paradox. So the next time someone says black holes just suck, you can politely correct them and tell them about how these monsters actually illuminate the universe. Anyways, if you want to dive deeper into black holes or quasars or any other astrophysical things, and even talk about astrophysics news, be sure to subscribe to the channel and click the bell to keep up with any uploads that I make. Anyway, thanks for watching, guys. Keep expanding your universe, and see you next time.
Don't forget to like and subscribe. It's free, and you can change your mind at any point in time, and it really helps me out as well.